Hello, students. I hope your family is well, and I hope you are well. Um, Stay healthy. We're going to look at today the mean value theorem, and this is from section 3.2. We're going to try to hit section 3, the highlights of chapter 3, and get into integration next week. So first we have to do the mean value theorem. The mean value theorem is a very significant theorem in calculus. And it could be that you won't find it the most useful until you get into some higher level courses. But it's important to know. So the mean value theorem says, suppose we have a function f that's continuous and differentiable. So it's continuous on a closed interval AB and differentiable on the open interval AB. So let me draw one. Let me draw a function that would work. How about we say it looks something like this? Oh, I don't know. I'll do that. So on the interval a to b, the closed interval, it's defined throughout, it's continuous, it's differentiable between a and b, no problem there, it's a nice smooth curve. Remember, it would not be differentiable if there were gaps in it, if it were not continuous, if there were gaps in it, or if there were points, edges in it, corners rather in it, then it would not be differentiable. So what the mean value theorem says, if we look at the secant line that joins the two endpoints and look at the slope, so the slope of the secant line would be f of b minus f of a over b minus a. The slope of the secant line, that's what it is, change in y over change in x. Well, it looks to me like, and it should look to you, that there's at least one point inside A and B where the tangent line is parallel to that secant line. So let's say it looks to me like it might be right there. So if I draw a tangent line right there on the curve, it looks like that slope is the same as the slope of the secant line. So in other words, we're saying that there's a C inside A and B where the slope of the tangent line is the same as the slope of the secant line. That's the mean value theorem. There's a special case of the mean value theorem, and it has its own name. It's called Rolle's theorem. And it says that if f of a equals 0 and f of b equals 0, so if these two endpoints are flat on the x-axis, then somewhere between those 2 points there's got to be a place where the derivative is 0. Okay, so in Rolle's theorem it puts another condition on the values of f at a and f at b, and they have to be 0. But it's really just a special application of the mean value theorem. Okay, so let's look at how we might apply the mean value theorem. Specifically, the classic way to apply the mean value theorem would be problem 14 from 3.2. From chapter 3.2, number 14. In number 14, they give you a function on a closed interval. So in this case, it's the function 1 over x on the closed interval 1 to 3. And they say Okay, verify that this satisfies the mean value theorem. Well, it's continuous from 1 to 3. It's not continuous at 0, but we're not anywhere near 0. It's differentiable from 1 to 3. How do we know? Well, f prime of x, this is the same as x to the negative 1. So if we bring the negative 1 down, we would have negative 1 times x to the negative 2, which is negative 1 over x squared. And that's on this interval 1 to 3. That's fine. That's defined. No problems. So it satisfies all the conditions of the mean value theorem. Now we have to show that the conclusion of the mean value theorem works. So we look at f at 3 minus f at 1 over 3 minus 1. That's the slope of the secant line between the two endpoints. So we would get f at 3 is 1/3, f at 1 is 1, and then 3 minus 1. So we would get negative 2/3 over 2, which would be negative 1/3. Okay. So we know that the slope, what is that? The slope of the secant line is negative 1/3. Now what you would have to do when you're doing this problem is write these sentences out. You would have to say, this function is continuous on the interval, closed interval 1 to 3. It's differentiable on that interval. The slope of the secant line is negative 1/3. There must be a point between 1 and 3 where the derivative is negative 1/3. So we take the derivative, negative 1 over x squared is equal to negative 1/3. We have to solve that for x. Well, it's obvious that x squared has to be 3. And we're not using negative square root of 3 because we want to be between 1 and 3. So it must be that x is the positive square root of 3, which is between 1 and 3. So we've confirmed that, this is our C, our point where when we take the derivative of the function and put in square root of 3, we get the same thing as the slope of the secant line. So we've confirmed that. Okay. I'd like to do one other problem from this set, and that is problem 4. Problem 4 says, let me get something different. Problem 4 says, make up a function, sketch a function that's continuous on the interval from 0 to 8. And they also give you that f of 0 is equal to 1 and f of 8 is equal to 4. So it's continuous from 0 to 8. And f at 0 is 1, f at 8 is 4. Give me a function that does not satisfy the mean value theorem. Well, okay, so here's one endpoint, 0, 1. Here's the other endpoint, let's say 8, 4. So if we draw a smooth curve, that's not going to work, because that would satisfy the mean value theorem. We need something that's not differentiable between 0 and 8. Okay, how about a function like this? Let's say it goes like this, and then it goes like that. So it has a corner. Well, you can see, so why? Why is this doesn't satisfy the mean value theorem? Well, clearly this is one line. It has a certain slope. let's say it's a horizontal line, so the slope is 0. This is another line, has a slope that's a lot steeper, bigger than this one, and it's not differentiable right here, right? Because we have a point. So here's a case where there's no c between a and b, between 0 and 8. There's nothing in between there where the derivative of this function is equal to that, is equal to the slope of that tangent line. There isn't any. So this is a good example of a function that doesn't satisfy the mean value theorem because it's not differentiable throughout the interval 0 to 8. Okay, problems from section 3.2, and I will copy the pages out of the text and put them on Moodle. But the problems from chapter 3.2 are, let's see, 3, 4, 6, 11, 13, and 15. And I'm also going to post a video about the second derivative and the first derivative and what it tells us about a function. And I'm going to assign more problems from that set. That'll be due Tuesday night. Okay, talk to you soon.